Hey everyone, welcome back to part two. In part one, we went over energy level diagrams and the arrangement of the electrons. So which orbitals they fill and the subshells in which order, because it's based on proximity and energy. And we left off with the staircase pattern, which told us the order of the energy level and orbitals that get filled. And then we did some examples. So we're going to pick up from here at electron configuration. So there are clues in the periodic table that help us determine what an element electron configuration is. So where the electrons are, where the high energy ones are, where the low energy ones are. So we're going to learn how to do that from there. So one of our last examples was the zinc atom, which is Zn. So this has 30 electrons. Okay. So as a quick recap, if we use the zinc atom as an example, and we fill this energy level diagram based on the off-ball principle, we should follow it like this. We're going to keep going, and we're just counting as we go. So at this point, we fill 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. And again, it's filled based on energy level. Okay, so 4s before 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, if you're good at mental math, you can kind of see that there were 5 spots at 2 electrons each, so we'll go from there. So this is a finished energy level diagram for an atom, and we had said ions lose from the highest energy level, not the highest energy orbital. So that's an important distinction to make, and I talked about that near the end of part A of this series. So what the electron configuration is a horizontal explanation. So the energy level diagram is vertical, and electron configuration is just writing out all of our orbitals with the number of electrons in them. So for zinc, we have the 1s orbital, and there are 2 electrons in it because there's 2 arrows. So we get a little superscript 2. Then is the 2s orbital, and again, that has 2 electrons in it because it's filled. After that comes the 2p orbital, and there are 6 there. And I'm just going from the bottom up. Then there's the 3s orbital, and it has 2 electrons. Then there's the 3p orbital, which has 6 electrons in it, based on our diagram. That's what we're looking at. Then we have our 4s orbital, which has 2 electrons, and our 3d orbital, which has 10. So this is what the electron configuration is. All right, it's based on the energy level diagram, only it's written out horizontally. Now, if we look here, notice how these orbitals are not together. You think, well, the 3d orbital is not past the 4s orbital. 4 is the valence shell, which is correct. Don't forget this is based on energy. It's not based on distance here. Okay, so they won't necessarily be 1, 2, 3, 4 because they're based on the staircase pattern and the order that they show up in. Okay, so that's what electron configurations are, just condensed ways of writing energy level diagrams. So now we're going to go through some shortcuts. How can you get to this without actually drawing an energy level diagram? So they're useful for seeing the arrangement of the orbitals, but once we get past that, what we're really interested in is where are the electrons, because that's how we're going to determine what the reactions are that can happen and the type of ions that can form. So we can shorten this. What we're going to look at, right, is this first underlined section here. So to shorten that, every atom can be thought of as the atom before it plus another electron. So hydrogen has 1 electron. We can think of helium as a hydrogen atom with another electron and proton. So all we're going to do is use the periodic table to help us simplify this. So we're going to rewrite an element in terms of another element so that we don't have to show so many electrons. So the noble gas from the previous period is always our reference point because we know that that had a full shell. So if you find zinc on your periodic table, right, the noble gas that's before zinc, if you want to have a pause and look at it, and if you looked, the noble gas should be argon. So to write zinc's formula, we can say, well, it's really an argon atom, right? And if we count how many extra electrons there are, argon has 18 electrons. Zinc has 30 electrons. So there's a difference of 12. Right? So it's an argon atom plus an extra 12 electrons. Now, if you count up how many are here, you'll notice that there's, excuse me, there are 2 electrons in the 4s orbital, 10 in the 3d orbital. That adds up to 12. So this is called the noble gas configuration, or the shorthand configuration. Okay. So that's how it works. Now, how do you actually figure out what this is? So to know how many electrons to replace, that's the key. Figure out the noble gas that's before your element. So in this case, argon was our noble gas before zinc. It's before everything in that row. So that's our starting point. Then look at, so step 1, identify the noble gas that you're working with. Step 2, identify the period that it's in. So in our case, it was argon. Argon is in period 3. Okay. Now, on the periodic table, we're going to pull up an image of this in a second. It's broken into what are called blocks. Okay. And what the blocks tell us is where the last electron is in that element. So if I scroll forward here, I'm going to have a periodic table. All right. Argon is right here on the periodic table. So that's called the P block, all right? And it's broken up by color. So the first 2 columns are known as the S block, and that means the valence electrons are in the S orbital for these elements. The transition metals are called the D block, which means their valence electrons, right, fall in the D orbital, depending on the period that they're in. So we'll say valence electrons fall in D orbital. So argon's what's known as the P block. And there's really only one exception to this rule, and that's helium, which even though it's on the right-hand side, it's part of the S block. You can kind of see it's missing from there. So this is the S block. This is the P block, and you can see the green with the green part is the F block. So argon being in the 3rd row and the P block, okay, and then we look at 1, 2, 3, 4, 5, 6, its position in the P block, that tells us where argon's valence electron is. Okay, so the next electron after argon is in the 4th period, in the S block, in the 1st position. So that next electron will be 4s1. And what's fun is that the periodic table is actually organized according to the staircase pattern. So argon, 3rd energy level, so the 3rd row, in the P block, so it's 3p. Its valence electron is in 1, 2, 3, 4, 5, 6. So argon has 6 electrons in its P orbital. The next element on your periodic table is potassium, K. Potassium has 1 valence electron, and that's in the 4s orbital. Okay. Calcium has 2 valence electrons. They're both in the 4s orbital as well. Now going back to argon, you might think, well, it doesn't have 6, it has 8 valence electrons. Yes, they're in the 3rd energy level, split between the S and the P orbital, because don't forget the S can hold 2 electrons and the P can hold 6. So if we go back to zinc now, zinc is over here. So after we fill argon, so again, the noble gas before zinc is argon. It's in the P block, the third energy level, in the 6th position. So that's what we're going to replace with argon, and the rest of the elements stay the same. So I'm going to go back to this example. What you'll notice, so in this case, it was the P block, and it was in the 6th position. So, in general, how do you know what to replace? You're going to go replace everything up to the last P orbital with the noble gas. And then the rest of the electron configuration can stay. And we'll do some examples with this. Okay? So rewatch that explanation if you need to. The next one might be a little bit shorter to help out now that we've gone through it. So let's use sulfur as an example. Sulfur atom. If we look at our periodic table, right? We might think, okay, now I have to draw an energy level diagram and remember the staircase pattern. Not the case. If we write down every energy level and block that we pass, we'll build the electron configuration. So, what we're going to do, I'm going to keep going from here. We start at the beginning. 1s1, 1s2, 2s1, 2s2, 2p1, 2, 3, 4, 5, 6. We're passing all of these, so we're assuming these orbitals have to be full until we get to sulfur, which is right here. So we're passing the 1s orbital, we're passing the 2s orbital, we're passing the 2p orbital, we're passing 3s, and we're stopping at 3p4. That's its position here. So 1s filled, 2s filled, 2p was filled, 3p was filled, and then we stopped at 3p4. So again, the periodic table helps us with that. Now the shorthand configuration. So we replace it with the noble gas that's before it. So if you look at your periodic table, find the noble gas that's in the row above sulfur. And you should see that it's neon. So to write the shorthand, this is considered the full electron configuration. We're going to do the short example. I'm going to replace everything up to the last filled p orbital. So I'm looking for a p6. That's my clue that that's where it stops. Now if I look at it, neon is in the second row, in the p block, at position 6. So all of that gets replaced with neon, and the remainder stays. Okay. Now if we add all of these numbers up, right, 2, 4, 10, 12, 18, that's how many electrons sulfur has. 2, 4, 10, 12, 16. Sorry. Just threw an extra 2 in there. 2, 4, 10, 12, 16. Right. So the numbers on the orbital designations should add up to the total number of electrons. Right. So that's one example. Now let's try identifying this element. Okay, so based on the periodic table, here are all of the orbitals that have electrons. So there's a couple of ways we can do this. Number one, let's look at the total number of electrons. Okay, it doesn't look like there's anything missing, so it's not an ion. So I've got 2, 4, 10, 12, 18, 20, and 28. So which element has 28 electrons? Okay, and it should be nickel. Now, to confirm that, let's look here. Now we're told it's an atom. If it was an ion, that would be a little bit trickier. We'd have a little bit more investigating to do. But everything, there are no missing electrons here. Okay, we're told it's an element, so it's not an ion. So let's go to the third energy level, the D block, and the 8th position. And that'll tell us where the last electron is in that element and give us a hint to its as to who it is. So if I go to my periodic table, Notice how the d block is beside the 4s orbital. So 3d 1, 2, 3, 4, 5, 6, 7, 8. And if you have your periodic table with you, that is nickel. Okay, so 3d8 equals nickel. So these electron configurations are useful because it tells us where the valence electrons are, how much energy they have, and it gives us hints as to what the ions that can form are. So if we tacked on to this, before we go on, this is an element. If I asked you to write the electron configuration for the ion, right? So let's do an extension here. The nickel ion, let's say we're using the 2+ ion. Okay, so if I have to lose 2 electrons, ask yourself, where would that be from? And if you've paused and had a chance to think about that, let's go through it. So nickel is going to be 1s2, 2s2, 2p6, 3s2, 3p6. We're doing this for the ion. You should have removed the 4s electrons because those are the farthest. They're valence. They're not highest energy, but they're the farthest from the nucleus, and they get taken first. All right, now if we wanted to write that in noble gas configuration, we go up to our last p orbital, right? And we look third energy level, and that is the noble gas argon, 3d8. So nickel has 4s2, 3d8 at the end. The nickel ion has just the 3d electrons, not the 4s. They've been lost as the valence electrons. So we'll take one more example here. Feel free to pause. And if you have paused and you're just reviewing this now, we're looking at the chlorine atom, which is by itself. So a chlorine, I'm going to make a note. It has 17 electrons. It's in the third energy level, in the p block, in the 5th position. So I can fill all the orbitals up to that point now. So 1s2, 2s2. 2p6, 3s2, 3p5. It's not 3p6 because it doesn't have 18 electrons. Now the shorthand, I'm going to replace all of that. Okay, the last filled p orbital with neon, 3s2, 3p5. Now, if you think about it, chlorine as an ion, let's just do another little extension here, is 1-, means it gains 1 electron, which means if it gains it, which orbital does it go to? And again, pause and think. Okay, so that 1 extra electron can't go in the 3s orbital because it's full, so it has to go in a p orbital. So it becomes 3p6 as an ion. All right, so we've got an electron configuration for the calcium ion now. 2+ means lose 2 electrons. So let's look on our periodic table. Calcium is in the 4th energy level. It is in the s block. Okay, so that means its electrons, so we're just looking at calcium here. And it's in the 2nd position. Okay, so that means 4s2 is how many electrons it would have. So we'll start with calcium. So we're going to fill everything based on the staircase pattern up to that point. 3s2, 3p6, 4s2. So as an ion losing 2 electrons, it's going to lose from the highest energy level. It'll lose all of those, both in this case, because it has a 2+ charge. 2p6, 3s2, 3p6. That's the ion. Now, if you write the shorthand configuration for that, notice how all of those get replaced, right? And it has the same number of electrons as argon, which is 18. So we would leave that in brackets like that. So those are two ways of writing electron configurations for an ion. Sometimes an ion is just using the noble gas. It's not the same because they have different number of protons still. Don't forget that important property. So having gone through all of those examples, again, here's the organization of the table. There's the S block, the P block, the D block, and the F block. And that kind of gives us a hint as to where the last electron is going to be in an electron configuration. And things can move around from there. All right, so go back and review that. If you'd like to go over counting, we can watch that again to hopefully help out. But for any element, for example, if we were looking at rhodium, which is in the 4d orbital here, right? We should know that, okay, the last, just as an example, rhodium, the last electrons will be 3d and 4d, sorry, and they're 1, 2, 3, 4, 5, 6, 7 in the 7th position. So I'm going to fill all the orbitals up to that, knowing that they get filled in order. Right? So I would say 1s2, 2s2, 2p6, 3s2, 3p6. So I'm just reading the periodic table to tell me what order everything is in. 4s2, 3d10. We're just going to go 4p6 because after 3d comes 4p. It gets filled with 6 electrons. Then 5s2. I'm going to cut myself short here. And then 4d7. Right, so that's how we use the periodic table to know how far up the energy level diagram to go and save us a little bit of time there with electron configurations. All right, we mentioned this. This is just the order that we go from left to right, top to bottom. So there's a cleaner version of that. If you were to look at the periodic table with the F block inserted, here's where it goes. So and this is important because in this value here, it appears to go 6s5d, and you wonder, well, where can the electrons go? But in reality, it goes 6s 4f 5d, and that is also in the staircase pattern without going back too far. Right, that's the order. So it goes from S to F to D after the D orbital. So we've got S, F, D, and P. Okay, and then it goes back to 6P in this case, if we're looking in that 6th row. So everything is in order. Here are some more examples. We can try these, write the full and condensed electron configurations by reading the periodic table. So for neon, right, its electron configuration, again, pause and try these. Okay. We're going to fill all of these up to 2p6 because it's in the 2nd energy level, p orbital in the 6th position. The fluorine ion, which means it's gained an electron, will be, okay, so fluorine is 2p5, but because it's gained one, it's going to be 2p6. Okay, that's interesting. Sodium ion is 1+. Just going to draw a little line here. Okay, so sodium loses an electron. It has 11. It's in 3s1. So if you take that electron away, it goes to 2p6. So there's sodium, the atom's configuration, but when it loses that electron, it loses from the 3s. So it becomes 2p6. These are called isoelectronics. Same number of electrons, different number of protons, and we've seen that before. Okay. So just to fill in here for nitrogen, I'll put the answers. You can pause, try them, and check against it. Now for iron, again, if you're watching this, I'm going to use the configuration here. I'm going to start with iron, just to show the difference for this. 4s2, 3d6. It lost 3 electrons, so first it loses the outer ones, and then it loses 1 from there. So this actually becomes argon 3d5. And then for nobelium, if you look at the bottom, that is element number 102 in the f orbital. So that's the last noble gas is given here as radon. And then we're going to go in order now for 7s2. We said next was the f orbital, so 5f. Oh, we've taken care of the 5f one. And then 5 after f. Sorry, we've taken care of the 4f. 5f. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So again, it's tricky, but remember, it starts in that order. Okay, so that one you might want to play around with before you check. So hopefully that helped. That's a lot of arrangement with orbitals and ions and electrons. So good chance to practice based on these questions in the Nelson 12 book. And hopefully this was helpful for you in your review.